It's working now. Yes. So you can attach that to the top down here, and then pull onto that, and the pointer if you wish to. Yeah. Yeah. We have the technology working. Okay. So, is it ready? I didn't see it. Is there a textbook? Okay. And so our next speaker is V.Chopovda, and she's going to be speaking on the planar periodic orbits arising from the Schubart-like periodic orbit in the Caledonian four-body problem.
Okay, so I'm V.Chopovda. I came here from New Zealand to make a talk about the planar periodic orbits that arise from Schubart-like periodic orbit. And I would like to start with a little background of my research, say the behind the idea that led to the idea of my project. So first of all, well, we all know that free-body systems are important, right? So there are lots of examples of those in the solar system, like Jupiter with its Caledonian moons, and on this picture you can see only 3 of them, but there's actually one more. And what's good about this picture, what I like about it, is that it was taken from Earth. And there are also examples in outer space, like say this system that has been discovered a couple of years ago in Centaurus constellation. So this one exhibits a binary star on one end, and another star with an exoplanet orbiting it on the other end, and the whole system rotates around center of mass. Okay, so in 1970s, Michel Henon explored a family of planar 3-body orbits that arise from Schubert orbit that was found by Schubert in 1956. So what is Schubert orbit? The Schubert orbit is that one. So this is a rectilinear collisional orbit, which has 3 bodies on the ends, and the second body acts as intermediary between these two. So the system starts with the collision of first 2 bodies and the other one outside from these two. Then the second body moves towards the third body and collide with that at half period, and then it moves back to the first body. So the whole system was generated by using angular momentum as a parameter of the system. And these are the orbits that he has found plotted in real coordinates. And because the system rotates about the center of mass with a constant angular velocity, it's worth putting those on a rotating frame that rotates with the same angular velocity, so that the coordinates at the start and end of the period are the same. A couple of decades later, Winston Sweatman, my supervisor, had found 4-body Schubart-like orbit with a family of quasi-periodic orbits that surround it. And so on this plot, well, this is the XY plot, the orbit is one-dimensional, that's why it's just a straight line, and the other plot is x against time. So what we see here is that 2 bodies on one side first collide, then the middle bodies go closer to the center of mass, collide one with another, and then they go back to meet the outer bodies. A few years later after that, Winston Sweatman has discovered a planar 4-body orbit which is relatively close to the equal mass Schubart-like interplane orbit. And that's how this looks like. So here each outer body orbits the inner body, and the inner bodies alternately pass one around another. And so the existence of these 2 orbits suggested that there probably is a similar family of 4-body orbits similar to the Henon studies, and that's what I've been working on. Yeah, and to be able to find all these orbits, I was solving the Caledonian symmetric 4-body problem, which was introduced by Archie and Winston in 1998. So in this system we have 4 bodies that move into planar orbits about the center of mass of the system. For this project, we assume that all bodies have equal mass and they're point-sized. So initially, these 4 bodies start on a straight line, and they have velocities perpendicular to that line. And we say that the start of integration time is when the bodies 2 and 3, the middle ones, are at extrema. This time it's maximum. This system has 2 kinds of symmetry. First is a past-future symmetry, which essentially means that integrating forwards is a mirror image of integrating backwards. The dynamical symmetry is that the dynamical behavior of 2 bodies on one side of the system's center of mass is a mirror image of the other 2 on the other side. We fix center of mass at the origin, and we've got conserved energy, angular momentum, we set the gravitational constant to 1, and the total energy of the system is equal to -1, and that's the Hamiltonian of the system. And because the Schubart-like orbit is a collinear orbit, we have to use regularization to be able to integrate through collision or close encounter. For this project, we use a Higgs type regularization of all the interbody coordinates of all 4 bodies. So this transforms every interbody distance using the KS coordinate transformation, and after that, we rescale time for the system, introduce transformed Hamiltonian and regularized system of equations. And then, by using angular momentum of the system as a parameter and also fixed and conserved quantities of the system, we perturb the outer bodies of the system, and we build an iterational method, an iterational process over that, and that's how we produce our results. And here they are. So the family starts with the Schubart-like orbit, which is this one. So all these orbits are plotted in fixed and rotating coordinates, same as before. As we add up angular momentum to the system, the orbits start to extend in y direction, becoming elliptic, and then circular. You may know that angle of rotation also grows. Well, in fact, the orbits first rotate counterclockwise, and then they change direction and start rotating clockwise. And also, the distance between 2 bodies on one side keeps on increasing. And all these orbits that you see tend, so they all result in what we call a semi-choreography orbit, which is a nice orbit. So we have 2 outer bodies that orbit, that are on one orbit, and 2 inner bodies that are on another orbit. And I'm pretty sure I came across this orbit in the literature, and it was referred to as a hip-hop orbit. What's also peculiar about that is that it has 0 angular momentum, and angular rotation of that is pi. And if we search for more orbits after that, what we'll see is that orbits start to repeat themselves. So if you look at these 2 orbits in, say, fixed coordinates, you can't really say that these are the same, but on the rotating plots, they are really the same orbits. Even if I show the animation, you can't really say that. Yeah. So in fact, the second orbit is the same orbit, but just plotted from half period. And it rotates in the opposite direction, so all the velocity vectors and angle of rotation and angular momentum, they're all opposite towards what we have in the first orbit. And so what we have after semi-choreography orbit is that all the orbits repeat what was before that until we get back to Schubart-like orbit. So we can say that this family starts with the Schubart-like orbit, then it turns to semi-choreography, and then it goes back to Schubart-like orbit. If we look at the variables of the system along the family, say the initial coordinates of the bodies x1, x2, x3, and x4, you'll see, well, first of all, the distance between 2 bodies keeps on increasing, and also the initial coordinates of the inner bodies decrease. Well, they decrease until that value, which is a semi-choreography orbit, but if you extend that towards Schubart-like orbit, they will go straight to the center of mass. And the coordinates of the outer bodies, they first decrease until a certain value, and then they start increase again. If you look at angular momentum of the system, it first increases until it reaches maximum, then it decreases down to 0 to negative value, and then back to 0, which is semi-choreography orbit. We've also checked the linear stability of the orbits, of the family of orbits, and we checked that by introducing symmetrical and non-symmetrical perturbations on the plane and out of the plane. And so we generated monodromy matrices, and we paired up conjugate eigenvalues of those to be able to produce stability parameters. And we say the orbit is stable when stability parameters are less than 2 in absolute value. So overall we've got 6 stability parameters, 2 of collinear type, 2 of transverse type, and some of them are symmetric, some of them not symmetrical, and we've got 2 vertical parameters. And so what we can say is that the first Schubart-like orbit is unstable. That was also shown by my supervisor. And it's unstable vertically, and so the first orbits are unstable vertically. Then orbits are again unstable, but due to collinear perturbations. And the very last orbits are again unstable due to transverse perturbations. So overall, the whole equal mass family is unstable, and we think this is due to the fact that the Schubart-like orbit is unstable. But because there are other mass configurations in a one-dimensional Schubart-like orbits that are stable, we strongly believe that there are other configurations for planar orbits that perform such interplay motion that are stable. And at the moment, we're in the middle of getting these results, and they look promising. So I would like to thank the Celestial Mechanics Study Group for organizing such a nice event and for financial assistance. Also, I would like to thank New Zealand Math Society for travel grant, and of course Massey University and both of my supervisors, Winston Sweatman, who's unfortunately not here, but he would really love to be here, and Robert McKibbin. Thank you.
And we have some time for questions as well. Yes?
Have you proven analytically the existence of this orbit and the stability?
Sorry?
Have you proven analytically the existence of this periodic orbit? Have you checked it?
No, I haven't.
How do you know this?
So the Schubart-like, the analytical existence of Schubart-like orbit was proved by, I'm really going to name, but it was proved, and there is a paper of that.
I'm asking about your results.
Yeah, so it hasn't been done yet, I think.
So it's numerical simulation?
Yeah.
Okay.
Yes?
Is there any unsymmetric but stable four-body system?
Probably yes, but it's just not the part of my research, so I can't say for sure.
Okay.
Question? Any more? Yes?
Thanks for your presentation. And I'm wondering, is there any relationship between the work you are doing with the Jupiter system?
With what?
With the Jupiter system, with the 3 big moons?
Oh, no, it was just a part of the story. And it's just a nice picture. I love to start with nice pictures.
Okay, thanks.
Any other questions? Okay. Well, thank you, Valerie.